MagnaDrive's variable speed coupling incorporates high-energy permanent magnets that are mounted in these two rotors and copper as a conductor attached to our motor shaft. The magnets are attached to our load shaft. Right now there's a 1-inch space between the magnets and copper, which means that I'm not going to induce a field in my copper. This is going to allow me to start my motor up uncoupled. Doing that means that I can actually reduce lock rotor currents in my motor, especially when starting high inertia loads. As I move the magnets closer to the copper by inducing a signal into this actuator, the field in the copper grows, becomes stronger, transmitting more of the motor speed into my load and more torque. When the coupling's fully coupled, there's still an 1/8 inch gap between the magnet rotors and the conductor plates. There's absolutely no connection between the motor shaft and the load shaft. So I'm not going to transmit vibration from my motor and into my load. So the bearings over here are going to last a lot longer. Same time, this coupling can be misaligned. The motor shaft can be parallel misaligned from the load shaft 200 thousandths of an inch. That 200 thousandths of an inch is not going to produce any vibration. In industry, 80% of equipment failure comes from vibration. 60% is due to misalignment. By eliminating misalignment as a cause for vibration, I'm going to extend the life of the bearings in your pump. Your seals are going to go, life is going to go up, and the bearing life of your motor is going to go up. I'm going to show you a payback just in maintenance in that respect. Now this coupling is designed to do variable speed and process control. By doing variable speed over throttling techniques, I'm going to save energy. And we're going to demonstrate on this pump energy savings using the coupling to control flow rate over a valve. Now what I'll do to start with is I'll run the pump at the motor at full speed, engage the coupling through this actuator, bring the pump up to full speed, and I'll throttle this valve back till we hit 100 gallons per minute. Flow rate will read out on this display here in gallons per minute. We'll look at motor energy in watts. So we'll look at the energy that the valve draws. And then I'm going to open the valve up, unrestrict flow, put this little controller in automatic. It will take control of the coupling, slowing the pump down till we hit 100 gallons per minute, and we'll look at the difference in energy. So the motor's running, and my load shaft is not, okay? I'll apply a signal at actuator back there. It's going to move the magnet rotors closer to the copper, inducing a stronger field in the copper, thus transmitting more speed and torque into my load. Now the coupling's fully coupled. I'm doing 11,400 watts at 325 gallons per minute. I'll pinch the valve back till we hit 100 gallons, and we'll look at the difference in energy. Right now I'm doing 100 gallons per minute through the valve. My motor's drawing 8,200 watts, creating a large pressure drop across this valve. That pressure drop's creating cavitation. Cavitation will damage this piece of equipment over time. So we'll open the valve up, unrestrict flow, put this controller in automatic. It now has control of the coupling. It's going to slow the pump down until we hit 100 gallons per minute here, and we'll look at the difference in energy. We're approaching set point. There's roughly 100 gallons per minute, and I'm doing 3,300 watts. The motor's spinning at 1,780 RPMs. My load's spinning about 600 RPMs. The coupling is capable of doing 100% turn down. That's something a variable frequency drive has a hard time doing. To demonstrate that, I'll slow this down. As you can see, I can run the pump at a very slow speed without ever changing the speed of the motor, without ever damaging the motor.